Hello. Am I audible?
Yes, sir. Assalamualaikum, sir.
Okay, then I think we can start our today's class. Is my laptop screen visible to you?
Yes, sir.
Okay. We can continue. Now, last lecture we have started discussion on neural network. As in our last lecture, I have mentioned about that is the neural network training. We have two phases. The first phase is forward propagation, and second phase is backward propagation. In our last class, we have already discussed about the forward propagation, and in this class, we will discuss about the backward propagation. The target of forward propagation is to find out the predictive value, predictive results. And the backward propagation is responsible for updating the weights, okay, or adjusting the weights. We have taken this example. This is the example data set. And in this data set, we can see we have two features, F1 and F2. And these are the class levels. Okay, so this is the classification problem. And considering there is the 1 and 1 as an input, so here this one is 1, here is also 1. This is x1, and if we consider this is x2. Okay, so input is 1 1, and then after forward pass we got the output here. And in our last lecture we have discussed about the equations of the forward passing, like how to calculate the hidden layer summations or hidden layer sum, and then after passing the activation function, this sum to the activation function, that is sigmoid function, we have utilized as the activation function. We got the hidden layer results. Similarly, for the H2 also, that is, we have to pass through the sigmoid function with H2, and we got the hidden layer results. Similarly, for H3 also, we passed through the hidden through activation function sigmoid function H3, and then we got the hidden layer results. Okay, and then these hidden layer results will be the input of the output layer neurons. So here we can see for the quick review, if you want to find out the H1, that is the hidden layer values or hidden layer summation, then what we have to do, the input times W1, that means the input is here X1, and this is the edge connected to the hidden layer. So the weight of the edge is W1. So X1, W1, and this H1 has also, this neuron has also another connection, that is this connection. So this connection is from the another neuron of the input, and that is X2. X2 times W4. Here the X2 times W4, and we will get the H1. H1 is the hidden layer summation. Okay? The hidden layer sum. So hidden layer sum H1. Similarly, we need to find out the H2, that is hidden layer sum 2. Okay, so H2. There is the X1 times W2, the weight between input layer neuron 1 and the hidden layer neuron 2. So that is W2. Here is X1 W2 plus X2, that means this one, and also this connection weight. So connection weight is W5. Here is X2 W5. And then H3, this is X2 times, so X1 times W3, X1 times W3, and X2 times W6. We got the H3. Okay? We got the H3. So H1, H2, and H3. So we got H1, H2, and H3. Those are our hidden layer summations. Then we have to pass these values to an activation function for the non-linearity, because these equations are linear equation, but world is not linear. So sometimes our data set we need to apply some non-linearity because of the classification of regression purpose. So that's why we need to convert these linear values to a non-linear equivalent utilizing some activation function. And there are several activation functions like the sigmoid activation, tan H activation, softmax activation, value activation. So here we have utilized the sigmoid of activation function. This is sigmoid of H1. We know that the sigmoid of any value, like sigmoid of any value G, is actually is 1 by 1 plus a to the power negative G. So this is called the sigmoid function. Okay, sigmoid function. That means sigmoid of H1 will be 1 divided by 1 plus e to the power negative H1. Okay, and in our previous lecture we have seen that actually the sigmoid is kind of the S-shaped curve. Okay, S-shaped curve. So that is non-linear. So after finding out the hidden layer results, so these are after passing through the sigmoid functions, we will get the hidden layer results. Then to find out the hidden sum, so here is the hidden sum. We can say this. Sorry, find out the output sum here. This is the output sum. The output layer neuron. So output sum. This hidden layer results will be the input, and then times W7. So here is the sigmoid of H1 times W7. Then sigmoid of H2 times W8, sigmoid of H2 times W8, and sigmoid of H3 times W9. Okay, so W9. Then we will get the sum or output sum. O sum is output sum. Okay? So that means output layer summation, output sum. Then again we have to pass the output sum through a sigmoid function that is called sigmoid of output sum. Sigmoid of output sum. Okay? To get the results, there is the predictive results. So here is the sigmoid of our sum. We will get the calculated or predicted value. So this is also we call result. So this is the predicted results. Okay, so we have this is the predicted results. Then initially what we have done, initially we assign the weights, this W1, W2 up to W9, random values. Okay, random values within 0 to 1. Within 0 to 1, we have just assigned some random values like W1, W2. This is the value of W1, that is 0.8. W2 is 0.4. So in this way, this is W9. Okay, W9 equal 0.9. And also considering this input is 1 and 1. Okay, so that means x1 is 1 and x2 is 1. X2 is also 1. Considering this input, now we have calculated the value of h1. So you can see this is h1. In our last lecture, I have discussed in details. So this is the h1, that is 1 is the value of h1, 1.3 is the value of h2, and 0.8 is the value of h3. So these are the hidden sum. Okay, hidden sum. Hidden sum 1 is 1, hidden sum 2 is 1.3, hidden sum 3 is 0.8. Now what we have to do, we have to determine the hidden results. Okay? The hidden results. The hidden results, just pass this h1 to a sigmoid function. It is sigmoid of 1. It is 0.373. It will be our hidden results. Okay, hidden results. So 0.73. 0.73. Similarly, pass the H2 to a sigmoid function, then we will get the hidden layer results of our second neuron, that is H2, the H2 result, sigmoid of H2. So it is 785. Okay, 785. And H3 will be the sigmoid of H3, 0.689, that is 0.69. So 0.69 you will get. Okay, now what we have to do, we have to pass these values as the input to our output neuron. And then we have to calculate what? We have to calculate the output sum. Okay, the output sum will be output sum. It will be 0.73 times 0.3 plus 0.785 times 0.5 plus of 0.69 times 0.9. So we will get the hidden sum, and we have calculated the hidden sum here. Sum is, sorry, and the output sum here, output sum is 1.235. 1.235. So we will get 1.235. So this will be our output sum. As you can see it here, there is the sum utilizing this equation. Here is the sum. The output sum will be 0.235, and then we have to pass this sum to a sigmoid function. Sigmoid of 135, it will be 0.77469. So you can see 775, 0.775. And then the results will be it is the sigmoid of 1.235. It will be 0.775. Maybe 775. So this one will be our output results or output results. So this is the predicted results. This is the prediction. But according to our data set, you can see this data set, the expected value in the output is 0. So the expected value, okay, in the data set, the class level here, the output is 0. But according to our model, the predicted output is 0.775. And that's why you can see we have the error. Okay, we have the error, and we will calculate the error. So the error will be target minus calculated. So that means we can see 0 minus the calculated will be 0.77. So it will be negative 0.77. Negative 0.77. Now in backpropagation, propagation, we have to start from here. At first, we need to calculate the error. So target minus calculate the error. The target of our backpropagation is we have to update the weights, these weights, to minimize the error. Okay, to minimize the error. These are the values. We have to update those weights to minimize this error. Error is negative 0.77. We have to minimize the error because the output, the expected output is 0, but we got what? We got 0.77. So that's why what we have to do, we have to minimize the error. But how can we minimize the error? So there is just only one way. We have to update those words because the input cannot be changed. We cannot change the input. Input is 1, 1. We cannot change it. So in these equations, in our forward propagation, we can see in our forward propagation, we have these equations, And we can see there is x1, w1, x2, w2. x1 and x2, those are just input. We cannot change the input. We only change the w to get finally the 0. Okay? So that's why our target is to change the w. Those w's are called the learning parameters. So that means all these w's here, those are our learning parameters. So for this basic and simple neural network, we can see W1 to W9, total 9 learning parameters. So that means we can learn those parameters or update the values of those parameters. Okay. So that's why our target now is to update those variables, those variables. And this is back propagation. It means that it will update like this way. Okay. So that means initially it will update the values of our last layer. So this one, and then the first layer. So this one. So that means it will update like this way, this manner, in backward fashion. So that's why it is called the back propagation. At first, we can see this one and then this one. Okay, this way. So, but the thing is, this one is W7, this one is W8, and this one is W9. Okay, so how can we update? How to know that? That is, we have to increase the value of W7 or maybe decrease the value of W7. How can we know that? That is, whether we need to increase or maybe the decrease. Whether increment will give us the less error or decrement will give us the less error. Similarly, for the W8 also, whether we need to increase these values or decrease the values. Similarly, for W9 also, whether we need to increase the value of W9 or maybe decrease the value of W9. So that is a big question here. Then how to determine? Okay? By we will study the gradient. Okay? Gradient. That means the gradient will tell us whether we need to increase or maybe decrease the variable values. So now the finally results. Yeah, so that means we can see the finally how we got the result. If you can see from here, the result. Result is actually sigmoid. This is the sigmoid of this output sum. So this is the output sum. Okay? This is the sigmoid of this output sum, or sigmoid of this sum. Okay. So the result, and from the result, this is the predicted result. And error, actually error, how to calculate the error? Error, we have calculated what is the original value, original minus what is the prediction, predictive results. Okay? The original minus predictive results. So that means if we can change the result, the error will also change. Okay, if we can change the result, the error will also change. But this result, how the result will be changed? If the output sum is changed, if this sum is changed, then result will also be changed. Okay, so that means if this output sum, this value is changed, if this value will change, then the result also change. Okay, so that means then how much change of uh, the, the output sum will change the result. At first, we need to determine how much we can change the sum to change the result, and then we will find out that is how much change of output sum will change the error. So for that purpose, we can see this is the S sum. S sum is the sigmoid of the sum. S sum actually the sigmoid of the sum is our result. Okay, is our result. The sigmoid of the sum. So now what we have to do, we have to take the derivative of this. Okay, derivative of this. The derivative of the sum, it is the derivative of the sigmoid this is sigmoid of the sum. So this derivative of the sigmoid of the sum, it will be d sum by d result. Okay? D sum by d result, derivative of the sigmoid of the sum. So we can see here, if we consider this is our sum and this is our result, okay, and this is our sigmoid of the sum. This is sigmoid of the sum. Then we can see this is our d sum and this is our d result. If we can just draw the tangent. Tangent is what? Tangent is the derivative of the sigmoid of the sum. So if we, this is our sigmoid of the sum. If we can just draw a tangent at this point, this is our derivative of the sigmoid of the sum. So it will be the d sum. Here is the d result. So d sum by d result. So that's why the sigmoid of the sum, it is d sum by d results. So that is a rate of change of sum with respect to result. So now d sum by d results, then how much it will change our error. The error is target results minus calculated results. Then we can see d sum by d result, that rate of change times our error. So usually we call this on a delta sum. Okay, delta sum or delta output sum, rate of change of our output sum. Okay. Now we can see one thing is very interesting here. That is sigmoid of the sum, or you can say derivative of the sigmoid of the sum. The derivative of the sigmoid of the sum, sigmoid is what? This is the sigmoid, 1 by 1 plus e to the power g. So if we take the derivative of this sigmoid, that is, you can say delta of our sigmoid function with respect to x, then this is the part. So we will find out that d of it will be the delta of our 1 by 1 plus e to the power minus of x. Okay? E to the power minus of x with respect to dx. So then what we will get finally, we can take the derivative. Okay, we know that is how to that is the determine the derivative of an equation. So finally what we will get, we will get that it is equivalent to d of x times 1 minus d of x. Okay, so finally we will get this, that is d of x 1 minus d of x. So that means derivative of the sigmoid function, it is it's easy to calculate. It will be the derivative, it will be the sigmoid of x times 1 minus sigmoid of x, 1 minus sigmoid of x. So that means if we want to find out derivative of this sigmoid function, it will be that the value of that sigmoid function, that is this is x and 1 minus derivative of x. What does it mean? It means that you can see that we have already calculated the sigmoid of this one, sigmoid of 1.235. It is 0.775. So if we want to find out the derivative of 1.235, it will be sigmoid of x, sigmoid of 1.235, then times 1 minus derivative of 1 minus sigmoid of 1.235. Okay, so this one will be the derivative of sigmoid of x. It means sigmoid of x is what? Sigmoid of x is 0.775. So this one, it will be the 0.775 times 1 minus 0.775. 1 minus 0.775. Okay, then we will get the derivative. Okay, we will get the derivative. So that means it's easy to calculate the derivative if we know the sigmoid. If we know the sigmoid, then the derivative of the sigmoid will be that sigmoid times 1 minus the sigmoid. So it's easy to calculate. So that means no need to calculate anything more. So that's utilizing the sigmoid, we can find out the derivative of the sigmoid also. Okay, so now we want to find out what we want to find out how much change we need to do here. That means how much change we need to do in W7 and W8 and W9 at first. And for that, we will utilize this, that is the rate of change. The rate of change of that is sum with respect to result, and that will also impact our, that is the error. Okay, error. So that's why we will utilize this. Now we can see there is so the output sum. How to calculate the output sum? The hidden layer results times our weight from hidden to output. Weight from hidden to output. So that means the hidden layer results. Hidden layer results. What are the hidden layer results? So these are the hidden layer results. The hidden layer results 0.73, 0.785, and 0.69. So those are our hidden layer results. We have multiplied these hidden layer results with the that is the hidden to output layer weights. So hidden, this is hidden to output layer. So these are the weights of hidden to output layer weights. So we have multiplied these two to find out what the output sum. Okay? To find out the output sum. That is the output sum. So here, O sum, output sum. To find out the output sum, and then pass the output sum in sigmoid function to find out the results or predicted results. Okay? So that means to determine the output sum, what we have done so far, the hidden layer results. So these are the hidden layer results. Actually, we got the hidden layer results also from the sigmoid function, sigmoid of H1, sigmoid of H2, and sigmoid of H3. And then we multiplied those R with the hidden to output layer weights. Okay, so that's the equation we have used so far. So that's why it is written hidden layer results time weight of hidden to output layer with these weights. Then we will get what? We will get output sum. Okay. So this equation we have already utilized to find out the output sum. Okay? Find out the output sum. Now, what we have to do, we will take the derivative of this equation with respect to W. Derivative of this equation with respect to W. So that means on that case, if we take the derivative of this equation with respect to W, then it will be here the hidden results times derivative with respect to W. So here we can see this is W, so it will be 1 equal D sum or delta sum, delta O sum by delta W hidden to output. Okay, so that means this will be the case. So if we take the derivative of this equation with respect to W, then this will be 1. So here is the 1, and this will be delta O sum by delta W. So that means we will get this one, that is the hidden results equal delta O sum by delta W. From here, we can find out that delta WHO equal delta O sum delta output sum divided by hidden layer results. Hidden layer results. So delta O sum. So that means this is the delta WHO. It means that rate of change of W from hidden to output layer weights. So rate of change of W, rate of change of W. We need to find out the rate of change of W. That means how much change we have to perform here. How much change we have to perform in W8? How much change we need to perform in W9? So that is our delta, the delta weight, delta change, the delta W. We will change the weight, just delta W, delta W. And how can we determine that? It will be delta O sum divided by hidden layer results. Now delta O sum is what? Delta O sum is delta output sum. So we can see that the delta output sum is derivative of the sigma of the sum times output sum margin error. How? We have already discussed it here. This is delta sum by delta result. This is what? This is the sigma of derivative of the sigma of the sum. So this is actually the derivative of the sigma of the sum. Sigma of the sum times target results minus calculated results. That is error. Okay, times the error. So that is our delta O sum. That is our delta O sum. So that's what we have written. Delta output sum is equal derivative of the sigma of the sum times output sum margin error. So derivative of the sigma of the sum, it will be that is our sum is 1.235. Our sum is 1.235. So we can see that the sum is 1.235. Already we can see that this is delta O sum. O sum. Output sum is 1.235. And then if we take the derivative of the sigmoid, then the derivative of the sigmoid, it will be 0.775 times 1 minus 0.775. If we multiply these two, then we will get a value. Okay, we will get a value. That means this one is actually, you can see it will be 0.775 times 1 minus 0.775 times, and then output sum margin error. Then what's the error? We have already calculated the error. Error is negative 0.77. Okay, negative 0.774 or 775. If we can multiply these three terms, then we will get the negative 0.13439. Negative 0.13439. So this is our delta output sum. Delta output sum. Now we can see that this is our delta output sum. We already got this, the delta output sum. We have to divide this by the hidden layer results. Then what are the hidden layer results? We know that the hidden layer results are 0.73, 0.79, and 0.69. From here, we can see these are the hidden layer results: 0.73 and then 0.785 and 0.69. Okay? So these are our hidden layer results. So we have to divide the delta output sum by these three values. So that's what we have written here. That is, this is the value. Delta output sum and then hidden layer results. These are the three hidden layer results. Okay, so we have to divide this one by this three values. That means this one by negative 0.1344 by 0.13105. You will get this value, and then negative 0.1344 divided by 0.78583. Then you will get this value, and then 0.699997. You will get this value, negative 0.1920. So these are our delta weights. These are our delta weights. The delta weights. So delta weights means the change of weights. The change of weights of these values. Change of weights of these values. So now we already know the delta weights. Now we have to find out the new W7, new W8, and new W9. After changing, what will be the value for that? So that's why it is written here. That is 0. The previous value. These are the previous values of W7, W8, and W9. 0.3, 0.5, and 0.9. Now the new weights will be the previous weights times the delta weights. The previous weights we can see 0.3 plus of the delta weights. The delta weights is negative 0.1838. So negative 0.1838. Okay, then we will get the new value, and for that the new W7 it will be 0.1162. This one. Similarly, we need to find out the new W8. So here is negative 0.1710. So for the W8 it will be 0.5, negative 0.1710. Okay, then you will get this value 0.329. 329. Similarly, if we want to find out the new W9, the new W9 will be 0.708. So these are the new words. So these are the new words. So that means in our next iteration, forward propagation, we will not utilize those values. We will use these values, okay, in our next iteration. So these are the updated words. Updated words. So that means instead of these, we will utilize this value in our next iteration. So this is how we can update the weights of hidden to output layer. So this is the weight from hidden. This is the hidden. So hidden H, and this is the output O. Okay, hidden to output. So here is the delta is to output. So we have already determined how much change we need here in W7, W8, and W9, and then apply those changes. So here delta changes, apply those delta changes, and we got those values. One thing I need to mention here, that is, we can see that is the delta weights directly we have subtracted from the original weight, but sometimes we utilize the learning rate here, learning rate. So that means instead of subtracting the full weights, we have to multiply these values with learning rate, LR. Okay, so that means the delta weights times LR, delta weights times LR. So learning rate. Learning rate can be like, you can consider 0.01 or something. How fast or how slow we want to pick the steps, okay, step size. So that is our learning rate. So how fast or how slow we want to change the weights. So that's our learning rate. So that's why we can introduce the learning rate. Specifically, instead, if we consider the learning rate, that is non-learning rate, it means you have considered learning rate is 1. If we consider the learning rate is 1, in many cases, you will not get the optimal value because it will overstep your optimal value. That means it will skip the optimal value. So that's why you will not get the optimal value. So that's why usually we utilize learning rate, some lower values like here 0.01, or maybe less than that 0.001, or maybe less than that also like 0.0001. Okay, learning rate. So that means it will increase the values of those variables slowly. So if we can increase the values, maybe you can say in larger steps, then there may be possibility that you will escape the optimal value. Okay, so that's why it's better to go slowly. Okay, so we have already got the new W7, W8, and W9. But still, we need to find out the new value of W1, W2, W3, W4, W5, and W6. But for that, we can see that actually these values, they don't have the direct relationship with the output, or we can say the result. So that's why we have to do it in two steps. Okay, two steps to find out that is how much change is required to update W1 up to maybe W6. Okay, W6. So now our target is to update those values from W1 to W7, and for that we will utilize again the equation. So this is the equation. This is the equation hidden layer results times WHO equal output sum. So this equation we have already utilized. That's the same equation. Here, this one. Okay, hidden layer results times W hidden to output layer weights equal output sum. So we have already utilized this one. So the same equation here. But previously we have taken the derivative of this equation with respect to W. But this time we want to take the derivative with respect to output sum. Okay, with respect to output sum. So take the derivative of this equation with respect to output sum. Then what will be the values for that? So output sum, it means the right hand side, we will get in right hand side just 1. Yeah, because we are taking derivative with respect to output sum. Then 1 equal, here is delta hidden results divided by delta output sum, because we are taking derivative with respect to output sum times our WHO. Okay, so we will get this equation. Then actually from here we can see it will be, we will get that is 1 by WHO equal delta hidden results divided by delta output sum. Delta output sum. And from here we can write that is delta hidden results equal, that means this value equal delta output sum. So that means here delta output sum by WH. WH. We can write it. So that's what it is written. Delta hidden results equal delta output sum by WH. So consider that this is kind of the equation number 1 or something. Equation number 1. Then now we know that the sigmoid of the sum from our previous equation, you can see here, there is derivative of the sigmoid of the sum. It is the delta sum by delta results. So delta sum by delta results with respect to the last layer. Okay, so last layer, that means in this layer we have already calculated the sum. So this is the sum, and then after taking the sigmoid of this sum, we got the calculated results. Okay? Calculated result. So that's why we have taken the derivative of the sigmoid of our output layer, and it will be the delta sum by delta results. But we have also calculate the hidden results, specifically utilizing the same principle. That means we can say these hidden layer results, actually we have calculated from sigmoid of the hidden sum. So these are the hidden sum. Those are the hidden layer summation, and we have applied the sigmoid function to these values, to find out the hidden results. Okay? Hidden results. So these are our hidden layer results: 0.73, 0.785, 0.69 hidden layer results. So hidden layer results actually we got from the sigmoid of hidden sum. So that's why we can write. So here is the sigmoid of the sum equal delta sum by delta results. Similarly, we can say that the sigmoid of the hidden sum instead of the sum, so hidden sum equal delta hidden results, the delta hidden sum by delta hidden results. Delta hidden results. Okay. In case of our hidden layer nodes. So that's what we have written here. That is sigmoid of the hidden sum. It's delta hidden sum by delta hidden results. Just instead of delta sum by delta results, we can say this is the hidden layer. So we can write it delta hidden sum by delta hidden results. So this one and this one. Now this is equation number 1. We have already got this. We can multiply the both side of the equation of this equation using delta hidden sum by delta hidden result. So this side we can multiply this side delta hidden sum by delta hidden result. This side also delta hidden sum by delta hidden result. So in both left hand side and right hand side, we can multiply both side by delta hidden sum by delta. So that means here is the delta hidden sum by delta hidden results. Here is also delta hidden sum by delta hidden result. You can see this delta hidden results, and here is the delta of sum WHO. WHO. So this is the equation number 1. We can multiply both sides by delta hidden sum by delta hidden results. So what we will get? So we will get this equation. Okay. So now we can see this is delta hidden results, derivative of hidden results. This is also derivative of the hidden results. Okay. So we can see that is the delta hidden results, and here is also delta hidden results. So we can see so these two derivatives we cancelled out. So what we will get just only derivative of the sum here. Okay? So here is the derivative of the hidden sum here. So this part, okay, this part we will get from here. So and other side, what we will get? Other side, in this side we will get delta output sum WHO. So here is the delta output sum WHO and delta hidden sum by delta hidden results. And what is delta hidden sum by delta hidden results? Actually, this is the derivative of the sigmoid of delta hidden sum. So that's why we have written here derivative of the sigmoid of hidden sum. So that means this one is delta hidden sum. Delta hidden sum. So how can we calculate the delta hidden sum? From the delta output sum, we have to divide that one by WHO, and then we have to multiply it by derivative of the sigmoid of the sum. So now we have to perform this to find out delta hidden sum. So that means the delta hidden sum, it will be the delta output sum by hidden to output layer weights times derivative of the sigmoid of the hidden sum. Okay. So now delta output sum, we have already calculated the delta output sum. Here is the delta output sum. Okay, I have calculated. It's negative 0.134. So here is the negative 0.134. And then hidden to output weights. So hidden to output weights, so these are the weights of hidden to output. Hidden to 0.3, 0.5, 0.9. So these are the hidden to output weights. And then derivative sigmoid of hidden sum. And what are the hidden sum? The hidden sum are just this 1, 1.3, and 0.8. So those are the hidden sum. Okay? So these are the values. These are the values of hidden sum. 1, 1.3, and 0.8. So that's why the hidden sum is 1, 1.3, and 0.8. Now we can see that 0.13 divided by 0.3, we will get this one. 0.13 divided by 0.5, we will get this one. And 0.13, 0.9, we will get this way. And then the derivative of the sigmoid of 1, derivative of sigmoid of 1.3, and derivative of the sigmoid of 0.8, we need to determine. The derivative of the sigmoid of 1, we will get 0.1966. How can we calculate that? The derivative of sigmoid of 1, we already know this. Derivative of the sigmoid of 1, actually, it is 0.73. Okay, 0.73. Then derivative of the sigmoid of 1 will be 0.73 times 1 minus 0.7. Okay. Similarly, derivative of the sigmoid of 1.3, we already know that it is 0.79. So this value 0.79. 0.79 times 1 minus 0.7. Okay. So that's why from here we will get 0.1966, and from this one we will get 0.1683. Okay? 83. Similarly, for derivative of the sigmoid of 0.8, it will be 0.69. So 0.69 times 1 minus 0.69, we will get 0.2139. Okay, so this is our delta hidden sum. So delta hidden sum. So delta hidden sum, now we have to multiply this one with that one, this one with that one, this one with that one. So finally we will get negative 0.088. There is negative 0.0452 and 0.0319. This one is our delta hidden sum. So delta hidden sum, we will get these three values. So that means delta hidden sum, we got these three values, delta hidden sum. But the problem is we are not actually trying to find out the delta hidden sum, but we need to find out the delta W. We need to find out here, this is actually W, weight of input to hidden layer. Input to hidden layer. So we need to find out the delta WIH, or you can say DWIH. We want to find out this, but already we got delta hidden sum. So that means the rate of change of the sum here. Okay, rate of change of sum. Rate of change of sum. Now, as I already mentioned, that actually we need to find out the delta WHI, but we have to do it two steps. The first step we have already, first step is done. That is delta hidden sum. We have already calculated delta hidden sum, rate of change of hidden sum with respect to the error. Okay, with respect to the error. Now, what we have to do? We have to do a little extra things. Okay. So utilize this equation. This equation is actually we have already utilized to find out the hidden sum. So we can see this is what this is input times W equal hidden sum. Okay, so already we know that there is H1. H1 is what? H1 is X1 W1 plus X2 W4. Similarly, H2 is X1 W2 plus X2 W5. Okay, and also we know that H3, the H3 equal X1 W3 plus of X2 W6. Okay, we have already done this. So that means these are the H1, H2, H3. Those are our hidden sums. And how we have calculated those hidden sums? Those are our hidden sums. The input, these are our input, and we have multiplied with the W. Okay, so input times W. That is, if we consider the input is a vector, and W is also another vector, like if you consider this one, input vector is our X1 and X2. So this is our input vector. And then our W vector for our first one is W1 and then W4. It's like this W1, W2, W3, and then W4, W5, and W6. Okay. So then we can see this is input and this is our W. X1, W1 plus X2, W4 is our H1. Okay. So then X1, W2, and then X2, W5 is our H2. So that's why this is the equation actually we have already utilized to find out H1, H2, and H3. So that's what we have written here. Okay, now we want to take the derivative of this equation with respect to W. With respect to W, we want to take the derivative of this equation. So if we take the derivative of this equation with respect to W, then what we will get? We will get the I, and we are taking the derivative of this equation with respect to W, so it will be 1 here, equal d h sum divided by d W input to hidden. Okay, so that is we can say it will be the d W I H will be d h sum delta h sum divided by this I. Okay, this I. That is delta W input to hidden. It will be delta hidden sum divided by input. Okay, that is I. We are actually trying to find out this delta WIH. So delta WIH, that means rate of change of this W. This W is actually W input to hidden layer. We have to find out the rate of change. The rate of change. So rate of change we have already got. How to calculate that? Delta hidden sum divided by I. We already calculated the delta hidden sum here. The delta hidden sum. We have already calculated the delta hidden sum. Then we have to divide this by I. So here is the delta weights. On that case, it will be delta hidden sum. So those are the delta hidden sum divided by the input I. So I is, in our case, the I is 1, 1. So here the 1, 1. Then delta weights will be 0.88. This one divided by 1. So that means these values. And then again, this one divided by 1. We will get this values. So this is 0.088, 0.0452, like this way. Okay, so that means we can see this one is actually our W7, the delta W7. This is our delta W8. There is rate of change of W8, not the W7. So it's W1. This is our W1. So delta W1 up to delta W6. Okay. So the rate of change of this W is negative 0.088. Similarly, up to this one, it will be negative 0.0319. Now, utilize this equation to find out the new values of our W1, W2, and W3. So these are the old values of our W1, W2, and W3 up to W6. And the new values will be here. We can see this is the 0.8 for the W1 plus the delta weights, that is negative what? Negative 0.088. 0.088. Then we will get this value 0.712. Similarly, if we want to find out the W2, it will be W2 the previous weight, here is 0.4 plus of negative 0.0452. 0.0452. Then we will get the new value. Okay? We will get the new value. So this is this is how we have to find out the new values of W1, W2, and W up to W6. So these are the new values. Instead of the previous values, these values, we have to utilize these values in our next iteration. Okay. So this is the completion of the first iteration, that is one iteration, forward propagation and backward propagation. Utilizing the backward propagation, we have updates or adjusted the weights so that the error will be minimized. Now, if we can start our second iteration, in second iteration again, it will start from forward propagation. The second iteration. So what we have to do, we have to utilize the new weights. So these are the new W1 to W6, and these are our new W7 to W9. So utilizing those weights, if we apply the forward propagation now, forward propagation. Forward propagation. So if we apply forward propagation now, then we will see that actually after forward propagation, we will get the predicted value, this one, 0.69. So this is our second iteration. In second iteration, if we complete the forward propagation utilizing the same equations we have already utilized in our previous forward propagation, that is the H1 equal x1 W1 plus x2 W4. So those equations, okay, if we apply, then finally we will get that the predicted results will be 0.69. 0.69. So this, so considering this, the error, what will be the error? The error will be the target is 0, and we can say the predicted value is 0.69. That means it is negative 0.69. The error is now negative 0.69. So previously the error and new error, this is the error in our second iteration. Error second iteration 0.69. Previously, what was the error? It is 0.0 minus 0.77. So that is the error is negative 0.77. Previously, it was 0.77. Error in our first iteration, it was negative 0.77. But we can see error in our next iteration is negative 0.69. That means error is reducing. Error is reducing. So that means from the first iteration to second iteration, we got a little bit lower error. So if we continue, then again what we have to based on this error, the rate of change of our sigmoid, and then the result and this error. So it will propagate those values to here, and based on that we will update the weights of this layer and weight of this layer. So then again we will see that is our error is minimized also in third iteration. In this case, maybe fourth iteration, error will be more minimized or more reduced. So if we can continue maybe 100 iterations or maybe 1000 iterations, then finally we will get that actually the target is 0. So we will get nearly 0. The value is nearly 0. So this is how the weights are updated. Weights are updated to find out that is the input and output matching, matched input and output. So learning philosophy we have used here is this is called the sequential learning. That means one input at a time. So we have just taken one input, and then we have to consider the next input like 0, 1. Okay? And then we have to consider the another input like 1 and 0. And then we have to consider another input 0 and 0. Okay, and then every time we need to update the weights. So this is how the weight will be updated in neural networks. And then finally, when you can see that for all the cases for 1, 1, for 0, 1, for 1, 0, and 0, 0, it will correctly classify, correctly produce the output 0 and 1. Then we have to stop the learning there. Okay, stop the learning there. So on that case, we can say training is completed. Okay, then for any test case, those weights will be saved or stored, and then for the stored or saved weight, if we just maybe the new values will be there like -1 and 0, so new value. So this is the new input. Then this input we will pass through this one, and then the saved weight are there. So just apply the forward propagation for the prediction. Okay, so there will be no update of weights in that case. So it will directly take those inputs and then utilize those stored weights or set weight and apply just the forward propagation there. Okay, so we will get the updated, we will get the predicted results. So this is how the neural network will learn. So this is called the sequential learning approach, but we have also the batch learning approach. Okay, that means not only considering just one input at a time, but we can consider also the batch. That means several inputs together. Several inputs together. So like if we consider about our input is X. Okay, in this case, we can see if we consider we have 4 features like F1, this is the F2, and F3, and F4, and we have 3 instances like this is instance 1, instance 2, and instance 3. We have total 3 instances here. The 3 instances. Okay, here is the 3 instances we have. So if we consider that, okay, all these 3 instances we will pass to our neural networks. Okay, all these 3 instances will pass to our neural network at a time. So then we will consider call this one as our batch processing. Okay, batch processing. So how to work in batch processing, we will discuss this one in our next class. So thank you for attending this class. Do you have any question on the lecture I have already given here up to this slide, maybe. Do you have any question, queries, confusion?
No, sir.
Okay. Okay, thanks everyone for joining this session. See you in our next class. Thank you very much.